Hi there, so my name is Jack Wardlaw. I'll be measuring Planck's constant using LED lights. So what is Planck's constant? Well, it describes the way particles that make up light called photons behave, and Max Planck discovered that energy can only be of a certain amount called quanta. And his equation shows that energy equals his constant, 6.63 times 10 to the negative 34th joule seconds, times the frequency of light to determine the energy of the photon in that light. So I'll be measuring it using LEDs and using two properties of it, the activation voltage and the wavelength of the LED. Because at the activation voltage of an LED, the potential difference or voltage is equal to the energy emitted in the form of light or a photon. I'll be using this equation, activation voltage equals h Planck's constant times c the speed of light divided by e the charge of an electron times 1 over wavelength. So using the equation y equals mx plus b, we can determine that there's no y-intercept and that the activation voltage when plotted on the y-axis and inverse wavelength on the x-axis will be the slope of Planck's constant times the speed of light divided by the charge of an electron, and we'll use that to determine the constant. So what's my research question? Well, what is the value of Planck's constant as found using LED lights? And I predict that my measured value of Planck's constant will be within 10% of the accepted value, and also that there will be an inverse relationship between the wavelength of an LED and its activation voltage. Why is this important? Well, Planck's constant allowed for the development of a lot of modern computer technology, and any advancements in quantum computing are usually based on the fundamental ideas discovered by Max Planck. Furthermore, colorblindness runs through the males in my family, and I'm personally colorblind. So based on the relationship proven here between activation voltage and wavelength, and thus color of the LED, the color of an LED could be determined without visually seeing the LED and just using other properties like its activation voltage. My independent variable was the color of the LED, and my dependent variable is the activation voltage. Things I controlled in this experiment include the manufacture of the LED, the lighting of the room I'm measuring the wavelength in, and the calibration of a spectroscope, as I bought a kit to build a spectroscope myself, so I calibrated myself using the manufacturer's guidelines, so I don't have to worry about a building error from the manufacturer. Materials were two 18-volt variable power supplies, a white, red, orange, green, yellow, and blue light emitting diode, 4 banana connector plugs, 4 alligator clips, spectroscope, digital multimeter, and digital camera. So first I measured the activation voltage of the LED by connecting the LED to a multimeter and a variable power supply. Then I turned up the voltage on the variable power supply until the LED turned on. I did this with the lights off so I could see it best. And at that bottom picture there, when the LED just began to turn on, I recorded the voltage displayed on the multimeter. I repeated this for the red, orange, yellow, green, and blue LED. And for the wavelength, I connected the LED to the power supply and a white LED to the other power supply. I turned off the lights, and I turned up the voltage to turn on the white LED until I could see. This was the white LED was placed behind the numbered scale inside the spectroscope, and I turned it up until when looking through the spectroscope, I could see the numbered scale in the dark. And then for the red, orange, yellow, green, and blue LED, I put them in front of the slit of the spectroscope, turned them on in the dark, and then put the camera up to the viewing hole of the spectroscope and pointed it at the numbered slit and took pictures of my data. So here are the results, and you can see there's various wavelengths for each different colored LED. And putting these on a table, you can see as activation voltage went up from the red to blue LED, wavelength went down from the red to blue LED. And the activation voltage had an uncertainty of 0.01 volts, and the wavelength had a varying uncertainty depending on the spread as seen in the previous slide by the LED. So when we graph this, we get a line of best fit slope of 1.287 times 10 to the negative 6 volt meters, and you also get a maximum and minimum slope that vary slightly in each direction. So recalling that slope is Planck's constant times the speed of light divided by the charge of an electron. When plugging the charge of an electron, the speed of light, and our slope in, we can get a value for Planck's constant of 6.873 times 10 to the negative 34th joule seconds. And I repeat this process for the maximum and minimum slope to give me an uncertainty of 1.266 times 10 to the negative 34th joule seconds. And then to find my percent error, recall that Planck's constant is 6.626 times 10 to the negative 34th joule seconds. So when doing the percent error, I get the 3.73% error from my measured answer. And my percentage uncertainty is 18.4%, meaning my final value could vary about 18.4% in either direction. In conclusion, there's an inverse relationship between the wavelength and activation voltage of an LED, and my final answer was only 3.73% different than the accepted value of Planck's constant, both of which are supported by my hypothesis. Some strengths of my conclusion include that I used a camera to record wavelength, making it very easy to analyze the data. The LEDs were from the same manufacturer, and I built the spectroscope myself, and I turned off all the lights while recording the data. The weaknesses were I had to add the white LED, which added some light into the slit of the spectroscope, and the LEDs had slightly cloudy bulbs, and the variable power supply caused the LED to turn on very quickly. If I were to do this again, I would purchase and test with LEDs with clearer bulbs, and I would test more LEDs to get a balanced range of wavelengths. Also, if I were to do this again, I would try it with colored lasers to see if it could get similar results, and I'm interested in extending my findings to figure out if any technology could be developed to determine the colors of LED using voltage, making seeing the color actually unnecessary. So that's it. There are my sources.